It's one small step for man, one giant leap for mankind.
The cosmos is also within us. We're made of star stuff.
The good thing about science is that it's true whether or not you believe in it.
Let us imperatively voyage out into the blackness of space to colonize new worlds across the cosmos.
3, 2, 1.
Who doesn't love a good black hole?
Specifically, what would happen if you fell into a black hole? So, I guess, do you know what a black hole is, or what causes a black hole, where a black hole comes from?
My understanding of a black hole is it's like it's basically like the most intense gravitational pull that there is. Like, it sucks in light and everything.
Yeah.
And I don't know how they form. Yeah, I don't really know anything. That's kind of what I know about them. I wouldn't say I know a lot.
Okay. Well, so stars form energy or create energy by smushing atoms together, starting with hydrogen fusing into helium and so on and so forth, fusing heavier and heavier stuff together until eventually they get to iron, which when you fuse iron together, it does not produce enough energy to keep the cycle going, and so it forces the star to collapse.
So that's what will happen to the sun eventually?
I think so.
Does it happen to all stars, I guess?
It does not happen to all stars. That's what happens to stars that go supernova, which actually, maybe next time or in a time or two, I'll do like segment on the main star sequence or on star sequences. But
a black hole is just, all black holes were stars to start.
Yes, I think so.
At least as far as we understand. So
yeah, I think so. It's possible that there were some started like by primordial forces, but I think as far as we know, all of them were stars. But anyways, so the star goes nova, and if it's big enough, it like part of it explodes inward as it's exploding outwards, and if it explodes inward with enough pressure and enough mass, it forms what you described essentially. Something from which the gravitational pull is so strong that light can't even escape it. And essentially what happens is once it gets crunched down small enough, it becomes, as far as physics is concerned, infinitely small, which means that as you add more mass to it, it doesn't inherently grow in size. It just continues to get more dense. And so it creates a place where space-time is completely bent and like broken into a gravitational well. Because like all things have gravity, right? Stars, planets, even, things as small as people have a gravitational pull and effect on space-time. Black holes sort of poke through it all the way. So, if you were to ever be able to see a black hole, one of the things you would note first is that you actually really can't see it. Because, like we said, light can't escape it. So it's not like any other object that we can experience where light hits it and reflects off of it back into our eyes. Any light that hits a black hole gets sucked into it. So you would note almost like a complete absence of something. Not even like, it's questionable if it would even look like a big black dot. Like, you know how Interstellar, they have the big black dot with the weird colored energy disks around it? Yeah. It might even curve like the light that approaches it from the other side around it, that light which doesn't fall in, and so it might appear as just the accretion disks around it.
Yeah, you're describing it according to what the human eye would see, though.
Sure. Yeah, and in all fairness, like, this is almost all theoretical. We know very little practically about black holes. There's none close enough that we can really study them. We've only just now recently started to image what we think are black holes.
So do we have pictures of them or have evidence of them? Or
So this kind of gets into a little bit of nitpicking as to what you define a picture. We have representations of what they might look like to certain bands of light, if that makes sense. But it's not like we've like
it might
taken
not be something that's like visible, really.
Right, yeah, so we can like see certain gases and certain collisions of certain gases, which can tell us like
everything we see is because of light. Like, so if there is no
right,
light,
but we don't see all of light though. Light extends far beyond what the human vision spectrum is.
Yeah.
And so it can be light beams, it's just light beams that we might not see. So it's like processed so we can see it and stuff like that. But it's not inherently like you couldn't go out and take a picture of it. And like nobody has that we would traditionally assume. But there are like generated images of it. But anyways, I digress. So you're falling in towards the black hole that you may or may not even see. And you notice that around you is, this accretion disk. That's something that Interstellar got quite right. Is as things get sucked into the black hole, there is a moment when they could still theoretically escape, right? If something were to come in and speed up their orbit, they might be able to create a trajectory that gets out. But as they're collapsing in, black holes, because they all form from stars, are all pretty much spinning. And they spin incredibly fast, kind of in proportion to like an infinitely small and infinitely dense mass. So these things are spinning really, really fast, and they have infinite mass, or not infinite mass, but infinite density. And so they tear up everything as it is pulled in, and they tear it up to like the atomic level, where it's like shredding even atoms. And it speeds crap up to like near the speed of light, fractions of the speed of light and stuff. So as you're falling in, you're probably going to get destroyed by all this stuff. But let's just say you're in a ship that has some kind of armor on it that can withstand that. And so as you fall inwards, you're going to notice a couple of weird things happen. So remember how we were saying like everything has an effect on space-time? And we mostly like to imagine that as like a flat space that has like a divot. So you got a flat space, which is space-time. You put a large mass on it like a star, and it bends inwards, right? You're going to animate
pictures and stuff.
Sweet.
Like I have been. So if you have any particular ones, but I'll look up stuff too.
Yeah, I don't have anything in particular in mind, but you'll be able to find animations for what I'm talking about.
Yeah, definitely.
But as that space-time bends, it creates a difference in the way it's perceived for that person in the well. And the deeper down the well you go, the stranger timey things get. So as you fall closer and closer into the black hole, what's going to happen is you're going to experience time slowed down by a lot. And so as you look outside, if you could observe it, you would see thousands, hundreds of thousands, millions of years pass. And what somebody outside of the black hole would see is you start falling in and then just slow down and slowly, slowly slow down, almost infinitely slowly fall in, which would kind of be true for that person out there. Because as you fall, keep in mind, you're giving light off of your body as it reflects off of you. But as you fall closer and closer to the event horizon, or the edge of the black hole from which nothing can escape, like once you hit the event horizon, you're definitely going in, you're past the accretion disk. So as you're falling through this accretion disk, all those light particles that fall off of you towards outside observers are also being pulled in, until eventually, once you hit the event horizon, those light particles cannot escape the black hole. And so as you hit that, it gets to a strange place where the photons may never reach the person who's viewing you, but they may never actually get sucked into the black hole. And so, like, somebody could move their head closer and see you, and then move their head farther, and you would just wink out of existence, which would be a weird experience. So, then, let's say you're about to cross the event horizon now. There's a couple theories on what could happen. One theory that used to be widely held is that you hit what's called a quantum firewall. So, a problem with black holes in physics is that they delete information. If something falls into a black hole, it's basically, as far as physics is concerned, its information is completely erased. And that cannot happen in physics.
It's like an eraser, basically.
Yeah, but the problem is
It's the universe.
if you let that happen in physics, all of physics like breaks apart really quickly. So we know that that can't happen. But black holes seem to prove that that does happen. So
Different physics inside of a black hole, probably.
this is true, but also this would create different physics outside of it, which we can't have. Which you're totally right. Physics inside of a black hole essentially breaks down. And like once you hit the singularity, which is the actual point in the middle of a black hole, we have no possible way to even begin to describe it. But this information paradox, it's called, which was a huge physics problem for a while, created a big headache. And one of the solutions was what's called a quantum firewall, which is basically as you pass into the black hole, right on the outer edge, there's this wall of destruction that as you fall into it, it shreds and destroys you completely. So that's one possible thing. Now, we largely suspect that that doesn't happen anymore, thanks to Stephen Hawking and one of his more famous papers and concepts, Hawking radiation, which I'll describe in a second. But so maybe you get shredded by the quantum firewall, but let's say you don't. If it's a small enough black hole, what starts to happen as you pass through the event horizon is the gravitational force of the singularity is so strong and magnified by so much that parts of your body start to experience the gravity differently. So like when you stand up on Earth, technically your head is experiencing less gravitational pull than your feet, right? Because your feet are closer, so they're getting pulled harder. In this black hole scenario, your feet are getting pulled hundreds and millions of times stronger than your head is. And so as you fall deeper in, the gravitational pull increases until it essentially squeezes you into a tube of spaghetti 1 atom wide that's like superheated plasma goo. And so this is another believed possibility of what happens when you fall into a black hole. You get squeezed infinitely small, well, 1 atom small, I guess, and then sucked in. This is probably the most painful thing, as, you know, since gravity is hundreds and millions of times stronger than it would normally be, you're experiencing this over, like, millions of years, essentially, for you.
Oh, it'd feel like an eternity, is what you're saying?
Potentially, yeah. Again, you know, yeah, hard to say.
Consciousness and stuff before that, but your body would, the process of your body doing stuff would take for.
This is all theoretical, of course, too, because you would be dead way before you got even close to this part of the black hole. The accretion disk would shred anything that could conceivably survive. But let's say you fell into a giant black hole, right? Because we're talking about a tiny black hole where the gravity may be like dissimilar in places. But let's say you fall into one at the center of like the Milky Way, because as far as we know, every single galaxy has a supermassive black hole in the center of it. That's what all the galaxy orbits, basically. So if you fall into one of those, because its radius is so huge, it's like essentially flat. Let's say you get to continue to fall into the black hole without being spaghettified. Once you cross that event horizon, first of all, like I said, all of physics breaks down, so who knows what the hell happens. But largely, we can surmise that space-time itself starts to wrap inwards. So once you cross the event horizon, even if you start traveling away from the center of the black hole, like let's say we have a spaceship that can start traveling away, and let's say it can even travel faster than the speed of light, which would be enough to escape the black hole, it still won't be able to escape because the black hole's gravity is so strong that space-time itself bends. So as you travel away, you're still bending towards the center of the black hole. And of course, if you move inwards, you're moving towards the black hole. And as you move outwards, you're still pulled downwards into the black hole. No matter what way you move, you're like going into the black hole at this point. So you get
quicksand.
Worse than quicksand. Even if you stop and float and don't wiggle, you're still going into the center of the black hole.
Sorry, bud.
So then you get sucked further and further down until, you hit the singularity, which is a point where it's almost pointless to talk about because we have no real set of physics to describe it. But presumably you would be totally squished at this point, and certainly all bits of who you are would be irretrievably lost. Even if somebody were to find some way to like reverse time and undo the black hole and turn things backwards, you will still be lost within the black hole. Your time has become different inside the black hole than the rest of the universe outside, and you are gone. The information of what you were is gone. Which, again, to sort of touch on that Hawking paradox, I just want to describe his elegant solution because it's kind of neat. So Stephen Hawking observed that there are particles that blink in and out of existence really, really fast and really, really tinily, and they annihilate each other really quickly. So they like pop into existence, one is the antithesis of the other, they float around for a little bit, and then they meet back up and annihilate. At the edge of a black hole, if this were to happen, one of them might get sucked into the black hole and the other would radiate away. And because this is a kind of common event in the universe, slowly but surely these black holes would eventually radiate enough of their energy away that they would be able to just kind of one day evaporate and disappear. Which, fun fact, that will be very likely the last thing that happens in the universe.
There's a black hole disappearing.
Black holes evaporating.
And then that's the end of everything.
That's the end of everything. That would be the start of the entropic age, which would be the end of time.
Everything everywhere all at once.
Yeah, it would be everything. Well, what's interesting to think about is everywhere, everything all at once is the same as nothing anywhere ever.
That's true.
It's because basically the end of the universe is just the end of information. Nothing is different from anything else in time or space. It's all the same in every direction for all of eternity. And so it's not to like, it's
Are
not
you telling
really,
me space is communist?
It's not really enough to say that like nothing will exist. Everything will still exist. It will just be meaningless in reference to anything else. But yeah, that's what happens when you fall into a black hole. Wow. And that's a little bit of black holes and how they'll be the last things in the universe.